Yeah, sure.
Thanks for the invitation, Zeding and Rui, and thanks for the kind introduction. Today I'll be actually talking about our recent results on exactly related to the engineered quantum systems approach to quantum information. The particular engineering we have in mind for this particular talk is what we call quantum reservoir engineering. And hopefully, the meanings of all these words will become clear. Please do feel free to interrupt during the talk. You don't have to hold back on questions. So, without further ado, let me actually just start with a very um, broad and 36,000 feet introduction of why we care about quantum entanglement and reservoir engineering. As I'm sure the audience knows, there are several applications which are very enticing for quantum information processing and quantum computing. It all started with quantum algorithms like Shor's factoring search and Shor's factoring algorithm and Grover search, quantum cryptography. But now, very recently, people have also thought about how to actually use minimal noise techniques for quantum sensing, metrology, and safe communication and encryption. So, the heart of almost every application you can think of in quantum information comes from quantum entanglement. So the quantum entanglement is, of course, a special kind of quantum correlations, which at least Albert Einstein found spooky at the time. Now it is everyday business in all labs. Um, so why is the quantum entanglement makes it so powerful? Because quantum entanglement is directly, in some sense, the reason for quantum complexity. So if you ask a computer scientist, what do you think about quantum computing? They'll say, oh, the reason I am interested in quantum computing is because it seems that it can be actually useful to crack some problems which I cannot do efficiently with just classical resources and classical computing. So this is the idea of having new classes of computing which lie outside the regular polynomial class of computing, which is this famous VQP class, so something which is strictly outside P and covering some region of NP only because you have quantum resources at your disposal. And exactly as I said, the Shor's factoring and Grover search actually does belong to this bounded error quantum polynomial class, which is strictly outside the bounded error part, the classical BPP class. And in fact, the question goes beyond that, even from the sense of physics, because many body quantum systems have a complexity in their ground states, which we do not think we can ever be able to, by construction, describe using classical computers. Because in fact, if we could, then there is no need for quantum computing. So there's some kind of a almost a cosmic censorship if you have a quantum compute, if you genuinely have quantum mechanics playing at its role at small scales, because it leads to new kinds of correlation structures which we cannot even describe. Unless maybe if you have a quantum computer, you can at least simulate them efficiently. So that is the idea of quantum computers violating even extended Church-Turing thesis. It's a tantalizing idea. At least to my knowledge, it is yet to be proven, and it has led to some very interesting questions in the context of cosmology and quantum gravity. So, for example, if you have a really complex object, uh, probably black holes, which we cannot describe, or at least do not have a complete complete theory of, maybe they even violate the quantum extended Church-Turing thesis. Right? So it's actually pushing the frontiers of knowledge in not just computer science, but also in physics and cosmology. Similarly, if you ask an engineer why quantum computing is interesting for you, they would have a much more grounded vision as compared to probably computer scientists or quantum gravity theorists, and they'll say quantum computing is inevitable. We know that things get small, they become quantum. And we are making things smaller and smaller because we want to pack more and more information processing power in our chips. So eventually, you will, whether you like it or not, be in a region where quantum effects will be useful. So instead of considering them as a liability, maybe we should just try to control them and learn to control them. That is the idea of quantum computing, quantum chips, or quantum transistors. And finally, if you ask the physicists, what do you think about quantum computing? They are a bit of party poopers. They would say, quantum computing is hard, it's interesting, but it's hard. And the reason they have this not so happy outlook in some sense, or at least in terms of its implementation, is because there are kind of conflicting requirements when we think of a quantum computer or a processor. We actually do want to control these systems like we control classical systems, and we want this control to be efficient and fast. But at the same time, we also want to protect them from outside agents, because any kind of interaction with outside degrees of freedom leads to a decoherence or the loss of information of quantum systems. So because of these kind of conflicting requirements, it's not at all obvious what can be the final uh, hardware model of quantum computing, and that's what most of the research is. And this is my cartoon version of saying why we what decoherence does. Suppose you have this quantum quarter, which is basically this ket basically shows it's a quantum coin. And in fact, if it's talking to outside agents or uncontrolled degrees of freedom, which we call environment, it basically collapses into either a heads or a tail. So it becomes a completely classical coin and you lose all the power of superposition. And it is basically these kind of decohering effects which ultimately limit the scale of computations that can be executed accurately by any quantum processor. And it gets particularly bad if you think about using entanglement. This was just a simple superposition of a single qubit or a single quantum system. There, as I already said on the first slide, quantum entanglement is the heart of almost every QIB application you can think of. Unfortunately, quantum entanglement is also the most fragile. These kind of entangled state or resource states are also most fragile to decoherence. Because if any partner participating in these entangled states decohere, the entire state is destroyed. So in some sense, that's the catch-22 with entanglement. We want entanglement because it's our primary resource for QI. But we also know that it is the first thing to go out of the window if you have any decoherence. So that is the primary outlook of quantum reservoir engineering, that can we actually somehow beat decoherence at its game. We can we harness correlations in noisy quantum systems? And of course, everyone wants to build a big quantum processor, fault tolerant, logical qubits. However, there have been several recent results from both industry and academia where people have shown that even these kind of noisy systems without full error correction can have interesting applications if you know how to control noise. So these are the useful applications before we can have access to a universal quantum computer. And maybe, in fact, these kind of ideas can give us a clue about how to get there faster if we know how to control noise better. So there are a variety of NIST platforms. I'm sure a lot of you might be familiar with all of them already, or at least some of them. These are all platforms where the idea is to have strong interactions, however, while preserving coherences. And I will talk very briefly about an implementation. We work very closely with superconducting circuit experimentalists and circuit QED. So these are the kind of circuits which you will again see in the talk. But the ideas which I'll be talking about, they are actually platform agnostic and in principle can be applied to any of these platforms. So let us start with a very quick introduction to what is the meaning of quantum reservoir engineering. So you know that when you have a quantum system, typically this is the kind of evolution equation which is the rho dot is minus I h comma rho. This is nothing but the Schrodinger equation written for density matrix. However, when the quantum system is not isolated, but it talks to these uncontrolled degrees of freedom, which lead to decoherence, we have to add an additional terminates evolution, which we typically call some kind of a dissipation or non-unitary evolution. And almost all efforts until about 2010 were focused on Hamiltonian engineering, which essentially means that somehow we should make our quantum system or quantum gates so fast, so accurate, that before these bad terms which are written in red have an effect on the quantum system, we are done with our algorithm. So that is the primary idea of dynamical decoupling or even gate-based quantum error correction, that you have some kind of an error which happens because of this term in your evolution of the quantum system. And then based on either some kind of an ancilla-based feedback, you try to correct for the quantum system or just decouple it using some kind of pulse engineering from the noise to begin with. Now, the quantum reservoir engineering takes a completely opposite outlook. Instead of controlling the quantum system directly, it says, why don't we actually control the dissipation or the environment seen by the quantum system? So it essentially means that you, by design, actually engineer some dissipation on the quantum system, which this is the orange term in your evolution, and this is what I call the good dissipation, and the red is the bad dissipation. And if this good dissipation, which you have actually engineered on the quantum system, is of the correct form and is it strong enough, then instead of actually destroying your quantum correlations, it can actually create it. So that is the idea of dissipation engineering or reservoir engineering, that you are actually engineering the reservoir of the quantum system, not the system directly. And there are several like in the theory speak, you basically can just get rid of all these terms. And what you actually do is just think of good dissipation as like the controlled dissipation which you have dialed on the quantum system, and bad dissipation or the red dissipation as the thing which is just God given to you. This is kind of the T1 or the T2 of the qubits, or some kind of other leakage error you might have introduced during your algorithm. And this idea was proposed theoretically in 2009, where they actually showed that you can actually perform you can not just protect states, but actually perform computing using dissipation as a resource. The prepared state is actually a stable state over indefinite time, and it's actually robust to spam errors, which is state preparation and measurement errors. So therefore, you can actually initialize your system. You do not even need to initialize your system. It will just get to the correct state and do the correct thing if you dial your dissipation correctly. And one nice thing about this idea is that you do not actually need any pulse engineering or complicated control. This is all autonomous. So you actually, so from an experimentalist point of view, it's a huge improvement in their quality of life, because they don't actually have to do very, very complicated pulse engineering. So because of these ideas, between 2010 and 2015, there were like a slew of implementations in several platforms, not superconducting circuits, trapped ions, all these ideas of these dissipation engineering. However, so let's take a closer look. Why? But there was a caveat, and let's look at the caveat. So what is the caveat? So let's look at what you actually want the dissipation to be. So imagine that I have a 2-qubit system, and so I have a 4-dimensional Hilbert space, and I want my system to remain in this target state, which is, let's say, some algorithmically useful state for me, or some kind of an entangled state. And now what I want is that I should set my quantum dynamics such that if I am in this state, I don't go anywhere. So for example, this 5-0 can be the joint ground state, and I do not want to decay from the state. So that is what the first condition is. So this is the first condition which tells you what kind of operators you need in your dissipation, such that, and those operators should be such that your target state, which is psi, is kind of a null state of your dissipation operator, which is typically called the jump operator. And it should also remain invariant under Hamiltonian evolution. So it means that this state should be an eigenstate of your Hamiltonian. So if these two conditions are met, then once you are in this state, the rho dot is 0. And you can just check it. It's a very simple linear algebra thing. So that these kind of states are called dark states. This is a word which we borrow from atomic physics. The other thing, which is actually more crucial, is that it's not good enough to remain in that state. The whole idea of dissipation engineering or reservoir engineering is that if you leave the system alone, it should get there. So as I mentioned, irrespective of how you initialize your system, if sufficient time has elapsed, you should find yourself in your desired algorithmic state, which essentially means there should be a route into that state to get from this cloud of states you don't care about, which essentially means that if the dissipation should be such that if it acts on the target state from the left, it should not give you a 0. So essentially means that the target state should belong to the right null space of the kernel of the jump operator, but not the left null space. So these two things, these two conditions make sense, hopefully, intuitively. However, what happens is if you have linear dissipation, which is what most of the qubit systems or experimentalists can do typically, both these conditions cannot be satisfied simultaneously. So there are, like, I won't go into details, but if you want, we can talk about it offline later, that there are too many symmetries in the system. So you cannot satisfy both these conditions. You can satisfy one of them, but then you will also lose the control. So you can actually not have a state preparation, which is while simultaneously protecting the state. So these are that's why this is a no-go, and that is one of the reasons that the earlier versions of dissipation engineering did what is called the approximate stabilization. So the point was that this is a problem. You cannot actually satisfy both the conditions you want. If you really want the exact target state, what if we don't exactly stabilize the target state you want, but something which is almost like that or close to it? So for example, that means that let's say I want a singlet state, and instead of stabilizing a singlet state directly, I stabilize a coherent superposition of singlet and a little bit of joint ground state by using what is called a symmetry breaking term. This was actually the initial proposals which were implemented in experiments. The problem with these kind of approximate stabilization schemes is that these schemes have an intrinsic error, which essentially means that if you push the perturbative coupling, this perturbative coupling to the ground state hard, because to improve the rate at which you are purifying the state, you also push the population out of the state. So what that means is that you can either prepare a very high fidelity state, but it takes very long time, or you can do a very quick protocol, but you will get a very bad fidelity of your target state. So essentially, what there is a trade-off between the speed and the fidelity of state preparation, which is what I'm showing here. So in some science, this is like the error times time is a constant. So you can only optimize one of them. And this constant is basically, I'll show you later, is set by actually your local decoherence. So that is the problem, that these approximate stabilization schemes have an intrinsic error, which was the reason that it was not it did not become a standard paradigm for like state preparation or autonomous correction. So that was the primary thing which we have been handling in our group for the past 3-4 years. The aim of exact entanglement stabilization is basically to have stabilization or entanglement protocols which have no intrinsic error, which so that they do not suffer from this trade-off. This essentially means, as I have already shown you, let's say if you take the 2-qubit example, you cannot do it in the data qubit space. You need an extended Hilbert space somehow. There was an emergency vehicle. So yeah, so the problem, the to actually have schemes with exact stabilization, you need zero intrinsic error. And as you can imagine, let's say if I want to do a Bell state, the minimal extension I can have is add one more level. So it means that I will have a 1 qubit and 1 qubit. I mean, that's the minimal extension you can have on a 4 level, on a 2 qubit system. And that leads to a 6-dimensional Hilbert space. Now, with a 6-dimensional Hilbert space, I can play this game that I can have a symmetry which is preserved in the qubit space so that I have my original conditions fulfilled, but it is not preserved in the extended space. So I break the symmetry, but in the extended space. And in fact, this is indeed possible. This is actually the circuit diagram of the circuit QD implementation of this, where we actually used people who know these circuits. These are called transmon qubits. There are 2 transmon qubits. It's actually a multi-level system. So you actually have you have 2 transmons coupled to a resonator, and this resonator acts as your engineered bath or an ancilla system. So you pump the entropy out of your transmons into the resonator, and you deliberately control the left transmon as a qubit, which is the first 3. So you use the lowest 3 levels of the left transmon, but you only use the lowest 2 levels of the right transmon. So you actually can simulate a qubit in this transmon coupled system. So this device was built by NIST Boulder. And in fact, they were able to run the scheme which we developed, which I just showed you here. And you can see they initialize their system in a joint ground state. They let the time elapse. and automatically the system stabilizes into an entangled state. In this case, they chose the phases such that it stabilizes into a triplet state, but it can also be a singlet state or whichever. Any Bell state can be realized. So here, they could get a fidelity of 84%, and the time it took to actually get to the 1 over E time of this stabilization trajectory, which was measured tomographically, was 340 nanoseconds. So I would like you to see the x-axis. You see the state remains stable for almost 50 microseconds or whatever the number of time they just got, probably bored and ended the experiment. But the T1 times or the T2 times of the qubits, which are the transforms, was just only 5 microseconds. So that is the nice thing about stabilization, that it actually beats the decoherence. Even though the transform native decay rates are much shorter, if you stabilize the stable state, it can remain there forever because it's actually the good dissipation which drives the dynamics. And in fact, as I promised, these are the schemes which should not have an error time trade-off. So this is a theoretical prediction where we actually show that if you increase the good dissipation rate, you can decrease both your error and time together. And in fact, they were able to actually confirm this experimentally, that the terminal fidelity of entanglement and the time it takes to get there, they could actually tune them together, and they did not see a trade-off. So in fact, this is just to compare with the state-of-the-art performance. Basically, if you find the cumulative performance metric, which is like the total error times the time to stabilization, you want it to be as small as possible. We actually find that this is around a factor of 5 to 10 better than the previous schemes. You can see that the previous schemes were, even though they had better T1 and T2s as compared to us, you can see even this 100 microsecond scheme or 10 microsecond scheme, they took much longer or they had worse fidelity. And the reason for that is the schemes have no intrinsic error. This is an exact stabilization scheme. So are there any questions at this point? If not, just raise your hands. So this was just a proof of principle. We wanted to see if we can do exact stabilization in terms of just experimentally, like realizing just simple what is available to circuit QED experimentalists in superconducting circuits. But then we started thinking about, can we actually extend this idea for large entanglement or large scale entanglement or multi-qubit entanglement? So now when we say scalable, what is a scalable quantum circuit? That idea is very, very well developed for gate-based control. However, what I just showed you in reservoir engineering, you're not doing any kind of pulsing or time series gates. What you are doing is you turn on a Hamiltonian anticipation which stays on, and the system autonomously corrects its errors. So basically, we had to actually first define what does it even mean to have a scalable reservoir engineering. So for that, first let us try to understand or recall what is the meaning of complexity or scalability in terms of quantum circuit model. So there are these notions of the total number of gates or the longest path you need to actually realize in a quantum circuit, which is called a circuit depth. Then the number of operations which per layer. So the number of gates you can do in parallel, those are in some sense, at least heuristically, that basically determines your circuit width. And usually the quantum circuits are considered efficient or scalable if the circuit depth doesn't scale too fast with the number or the state which you are trying to prepare. So for example, if I want to prepare an n-qubit G at Z state, I should not have gates which are exponential to the power n or a very fast polynomial. So in fact, that is the meaning of complexity in the quantum circuit model. Like there are many reasonable complexity quantum circuits which can prepare, let's say, an n-qubit GHZ with order n gates and maybe a W state with order log n circuit depth. So inspired by these ideas, we wanted to translate these ideas for continuous state preparation protocols, because that's what reservoir engineering does. It doesn't have a gate. It basically has Hamiltonians and dissipators and things like that. So what features should a scalable reservoir engineering protocol possess? So the first thing which you came up was that just like bounded depth circuits, you want bounded depth interactions, which essentially mean that your system, your Hamiltonians which is the system Hamiltonian and system Bath Hamiltonian. These are the Hamiltonians which you actually create interactions between the system and some environmental degrees of freedom. They should be constructible from simple building blocks. If I'm trying to make a very, very large quantum circuit, I should not have an interaction or a Hamiltonian which has a product of 10 operators, because no one can actually realize those kind of large depth interactions. Similarly, we want, just like circuit width, we need low degree polynomial scaling of resource usage, which means the number of terms you have in your Hamiltonian. Those should not grow too rapidly, and the strength of these terms also should not grow too rapidly with the system size. And finally, as I said, we obviously do not want any intrinsic error. So the ideal steady state should exactly be my target state. And there, besides being fast and nice, it actually simplifies the design of these protocols, because what happens is that sometimes the intrinsic error itself is size dependent. So if you have an intrinsic error, it might look like that you are doing fine if you're doing Bell states or 3-qubit GHZ or 5-qubit GHZ. But if you try to extend these schemes to higher number of qubits, they actually fail because the intrinsic error scales very poorly with system size. So we are going to commit ourselves to always having exact stabilization schemes so that there is no intrinsic error to begin. So the choice of the target state which we did for this study was the W state. And for people who do not know what this state is, it's basically a maximally entangled state, which is a perfect counterpoint to GHZ. So GHZ is like the maximally entangled state of n qubits, which is like 0 tensor n plus 1 tensor n. Whereas W state actually is a permutation symmetric state of a fixed number of excitations in n qubits. So imagine that you have n qubits and you have to distribute k excitations in n qubits. This is what a W state looks like. It's basically a permutation symmetric distribution of these k excitations. And they have lots of applications in quantum metrology. They are considered most robust states because unlike GHZ states where if you lose even one qubit, you lose entire entanglement. In W states, you have maximal residual entanglement in the presence of erasure errors. So even if one qubit gets erased, you have a lot of entanglement to play with. So that's why they are used a lot in quantum communication protocols. So why did we choose this state? The reason we chose this state, as I said, the number of excitations is fixed. So because of that, there is a real chance of designing protocols for these states which have bounded depth, which means that their Hamiltonians are not becoming more and more complex the bigger and bigger W state you are constructing, which is not true for GHZ. The other very interesting thing about W states, which is again very different from GHZ, is that if you calculate the decay out of a W state and study that decay as a function of n, what you find is that in terms of as n becomes infinity or very large, the rate remains bounded. So gamma minus is the local decay of 1 qubit and gamma z is the dephasing rate of 1 qubit, which essentially, and so if you have n qubits forming a W state and each qubit has its own decay and decoherence or dephasing channels, the n qubit decay W state decays at this rate. And as you can see, as n goes to infinity, it remains bounded. It doesn't scale with it. Whereas in a GHZ, the rate out of the state scales with it. So that is actually a huge benefit for QRE, because I already mentioned that for QRE, one of the conditions is that your good dissipation should be stronger than the bad dissipation. So since the bad dissipation remains bounded in system size, it's actually easier for experimentalists to reach this regime where you can actually dial a good dissipation rate, which is strictly greater than your bad dissipation. Because if your bad dissipation keeps becoming larger and larger with n, it's basically a losing battle. So another thing which we found with W states, which is actually, I think, is probably the first time this has actually been seen in continuous protocols, is that if you look at the n qubit W state, since it's permutation symmetric, you can actually write it down as a kind of a decomposed or W state, where you have a W state on the first k qubits tensored with the ground state on the remaining ones, and vice versa. So why is this important? This is important because it means that if I know how to stabilize a smaller W state, I can actually use this to stabilize a larger W state, because a larger W state is kind of a superposition of smaller W states on different partners. Of course, I do not want a collection of small W state. I only want one large W state. So what it means is that if I actually have, let's say, 5 qubits, and I want to stabilize them into a n qubit or 5 qubit W state, what I can do is I can stabilize the first 3 qubits into W3, and 4 and 5 will remain in the ground state. And then I can stabilize the remaining the 3, 4, 5 into a W state, and 1 and 2 remain in the ground state. But since the third qubit is shared between both the setups, the only state which both of these setups will agree on is the 5 qubit W state. So in some sense, it's kind of a Venn diagram approach. You actually create null states of smaller subsets, but then when they intersect, they only agree on the joint dark state, which is nothing but the n qubit W state. So what that means is that I do not need to dial the dissipation on all the qubits simultaneously. I can do it on subsets. And that is the idea, that you can actually use multiple baths coupled to subsets of qubits, and then have some kind of overlapping qubits, so that the overlapping null states basically select only the Wn. And here there is a small technicality which I won't discuss in the interest of time. The joint ground state can also be the null state, but that is an easy problem to fix, because I can just use a Hamiltonian such that the W state is the eigenstate and the joint ground state is not. And then I'm done. So using this kind of modular dissipation purification, so we can actually write this. We actually developed this kind of a graph-based language to actually find what is the minimum number of dissipation channels you need to actually purify an n-qubit state. So for example, in the phi, we find that you need a minimum of 2. So you actually have a dissipator on the first 3 qubits, which is basically this green triangle. And then you have a dissipator on the 3, 4, 5, and 3 is the common, which stitches them together. So by using a similar logic, we can actually write down the minimal set of dissipator graphs or hypergraphs actually of width 3, which will purify a n qubit W state. So for example, you can see interestingly for 3, 5, 7, and 9, you always have these kind of chain configurations. Whereas when you have even numbers, you can actually have loops. Like for example, in n equal to 8, you actually have this kind of a loop. Similarly, for n equal to 6, you have a loop. I'm showing you these until 9, but actually to find, these are not just any graphs. These are the minimal hypergraphs. You can always do more. But the point is, if you're trying to come up with most efficient hypergraphs which purify an entangled state, we had to actually do a numerical search, and it's basically a brute force search, because this is like a graph isomorphism problem, that you have to find the unique graphs which are minimum. But it's possible. So we were able to do it for at least, I think, up to 15 qubits. And then we actually compared the performance of these kind of modular purification schemes against global schemes. So what do I mean by global? Global means that all the 5 qubits are coupled to just a single oscillator, which means there are not multiple subsets of qubits. All n qubits are purified together. If all the n qubits are purified together, this is the standard way people do it in trapped ions and things like that. That actually leads to a maximally connected qubit graph. And these connections are not through the Hamiltonian. This connection is through the dissipation. Since all the qubits are seeing the same dissipation channel, they basically talk to each other through the dissipation. And then we can plot the stabilization time, the time it takes to stabilize and get to the W state as a function of system size. And you can see that we use 2 versions of Hamiltonians, which it's not important for this talk. But you can see in both versions, irrespective of what kind of Hamiltonian we use, the tau scales exponentially with system size. Whereas when we do this modular engineering, where we are actually doing subsets of overlapping dissipators, we actually get a tau which scales polynomially. So we actually have an exponential advantage by using modular dissipation. And in fact, this is one of those ideas which is actually very counterintuitive if you first think about it, that actually having more connections is bad. not having a maximal connected graphs is actually a better idea when it comes to performance. So in fact, in dissipation engineering, maximally on all-to-all connectivity is actually a bad idea. And in fact, then you can actually play more games for a fixed system size, like 5 qubits, and with 3 dissipators, which essentially means that we are purifying subsets of 3 qubits at a time. We were able to study this rate, which is basically the inverse of the time, as a function of the number of dissipators. So one can say, oh, you're cheating. You actually now have more number of dissipation channels. Maybe that's why your scheme is faster. And that's not true. So here, what I'm showing you is basically a distribution of rates, because again, as I said, we have to do this using several graphs. So we used all possible potential graphs of when you have only 2 dissipators. So it essentially means that you can connect those 2 dissipators on 1, 2, 3, or 3, 4, 5, and up to a relabeling of indices. It's a minimal graph. You can do this with m equal to 3, which means now instead of 2 triangles, you deliberately say, I'm not going for a minimal configuration. I'm going to use 5 qubits, and I want to connect 3 nodes at a time. So maximum number of connections is 5, choose 3. So starting from m equal to 2, I can go up to m equal to 10. And I'm going to study the tau as a function of different coefficients on these dissipators. So the distributions are just different coefficients or different strengths. And the dashed line actually shows the median performance. And you can see, in fact, the median doesn't increase with the number of dissipation channels. It actually has a kind of a non-monotonic behavior, which essentially tells us that it is not as simple as just having more dissipation is a good thing. You have to actually design the most optimal dissipation, and then that may not be maximally connected actually, or nor does it need to have a maximum number of hypergraph edges. And then finally, we confirm that these are actually indeed exact schemes. So for that, essentially what we want to see is that the error times time should remain constant as a function of n. Error over time should remain constant. And that's what we find up to within 15 or 10%, 10 to 15%, this remains constant. And the steady state error only scales with that. There is no intrinsic error of the scheme. The only reason steady state error is increasing is because tau is slowing down, but it is not slowing down exponentially, it is slowing down polynomially. So your error is just the local dissipation times tau, which essentially confirms our the third point, that these schemes should intrinsically have no error. The error is just directly proportional. The faster the scheme goes, the better the error gets. So that is what these plots are basically showing you. So actually, that with this, I will give you the primary conclusions of my talk. I hope that I have given you at least a small flavor of what it means to have exact entanglement stabilization. Basically, the idea that you want purification schemes where the error and time scale together. They are not anti-correlated. And in fact, there is a real chance of extending these schemes to multiple qubits without efficiently. And that's what we mean by scalable stabilization, where the performance metric, which is basically entirely set by your time to get to that state. As of now, we are working on extending these ideas to higher dimensional entanglement, like, for example, where you can entangle more number of degrees of freedom of the same number of qubits. There have been some very interesting results where you can mix dissipation with measurements, which are called these fusion measurements. And that can give you another factor, exponential factor. So instead of tau being n, it goes as log n. So that's another exponential enhancement. And then there are some new ideas where, anything which you can do with gates, can we do it with continuous dissipation? So for example, can you do quantum annealing using dissipation? Similarly, can we actually, as people who work on error correction know, almost all error correction codes, they assume that your errors are uncorrelated in time. What happens if your errors are correlated? How do you correct for those? There are no error correction codes for that, at least in the digital world. Can we actually do correct for these kind of errors using dissipation? So with this, I will just show you the people who actually did all the work. This is a huge shout out to all my group members, especially Emery, who did a lot of theory development, and Tristan and other experimental collaborators at BBN and NIST who actually experimentally implemented their ideas. And as I think, as it was mentioned in the beginning of the talk, I'm always looking for motivated postdocs and graduate students. So if you're interested, please do apply. Thanks again, and I'll take questions.